Hello and welcome to this video. In this video, we will look at how to create, execute and exit from a process. In order to create a process, operating systems use a technique called cloning. When a process, for instance process 1 over here, invokes a system call called fork, it results in the kernel being triggered. The kernel then executes the fork system call in the kernel space and creates what is known as a child process. Here it is referred to as process 2. The child process is an exact duplicate of the parent process. So, let us see how the fork system call works with an example. Let us say that we have written this particular program which invokes the fork system call. The return from the fork system call is p, and p is defined as an integer, and it can take values of -1, 0 or something greater than 1. So, when this particular program gets executed, the fork system call would trigger the operating system to execute, and the OS would then create an exact replica of the parent process. So, this would be the parent process, and the exact replica of this process is known as the child process. The only difference between the parent process and the child process is that p in the parent process is a value which is the child's PID. So, this value is typically greater than 0. However, in the child process the value of p equal to 0. So, when the OS completes its execution, both the parent as well as the newly formed child would return from the fork system call with their different values of p. In the parent process, the child's PID is greater than 0, therefore, the parent process would execute at this point these particular statements. However, in the child process, since the value of p equal to 0, the else if part of, that is, these green statements would be executed. Now, if by chance the fork system call fails, a value of -1 would be returned, which would result in this printf error being printed onto the screen. Now, let us see how this fork system call works inside the operating system. So, as we mentioned before, each process has 3 metadata stored in the kernel. So, one is the page table, second is the kernel stack, and third is an entry in the proc structure which is the process control block PCB. So, when the fork system call executes, a copy of the page table is made. So, this is corresponds to the page table of the new child that is being created. Similarly, the kernel stack of the parent process is duplicated as the child's kernel stack. Further, a new PCB entry is created corresponding to the child's PCB entry. In order to do this, first an unused PID needs to be found by the operating system. Then a state of the newly formed process or the state of the child process is set to new. Then several pointers are set in the PCB, such as the page table pointer, that is, the page table pointer would point to this particular page table. The kernel stack pointer would point to this one, to this newly formed copied entry, and pointers to trap frame and the context which are present within this kernel stack. Other information such as the files open, the size of the process, the current working directory, etc., are also copied from the parent's PCB into the child's PCB. Finally, just before returning, the operating system would set the state of the newly created child to ready. So, we see that at the start of execution of the fork, the child's state is set to new, while towards the end of execution of the fork, the OS would set the state to ready. So, why do we need this intermediate state new? So, what does new signify and what does the ready signify? So, the new state indicates that the PID, the chosen PID over here, has already been taken and the process is currently being created, but not ready to run. On the other hand, when the state is set to ready, it means that the various metadata within the kernel has been initialized and the process can be moved into the ready queue and is ready to be executed. So, with respect to the ready queue, the new process would have an entry in the ready queue, and whenever the CPU scheduler gets triggered, it may pick up this particular process and change its state from ready to running, and the new process will begin to get executed within the processor. Now, one important difference between the parent process and the child process with respect to the fork is that in the parent process, fork returns the child's PID, while in the child's process the fork system call would return 0. So, how does the operating system make this difference? So, essentially the return from the fork system call is stored as part of the kernel stack. So, when the fork is executed, the OS or the operating system would set the return value in the kernel stack of the parent process as the child's PID. Further, in the kernel stack of the child's process, the return value is set to 0. Thus, when the system call returns in each of these cases, each process, the parent process as well as the child process, will get different values of the return type. Now, one of the primary aspects while invoking fork is the duplication of the page table. So, we have the parent page table over here, and when fork is invoked, a duplicate of this page table is created for the child. So, what does this mean to have a duplicate page table? So, when we actually look at this particular figure, we see that we have two page tables which are exactly the replica of each other and have exactly the same entries. So, what this means is that both the parent as well as the child page table are pointing to the same page frames in the RAM. Okay, so, let us look at this in more detail. So, we have the parent process with its virtual memory map and the corresponding child process with its own virtual memory map, and each of these processes have their own page table. So, the child process page table is an exact replica of the parent's process page table. So, what it means is that block 1 in the parent as well as block 1 in the child point to the same page frame, that is 6. Similarly, block 2 in the parent as well as block 2 in the child point to the same page frame 13 as seen over here, as well as in the child's process page table as seen over here. So, essentially what we are achieving over here is that we have two virtual memory maps, one for the process and one for the child. However, in RAM we have just one copy of the code and data corresponding to the parent process. Both the parent as well as the child page tables point to the same page frames in RAM. So, let us look at this with an example. Suppose we have written this following program which invokes the fork, and fork returns a PID, and in the parent process we sleep for some time and then invoke printf which prints the value of I. So, I is defined as an integer which has the value of 23. Similarly, in the child process which gets executed in this else part, we again print the value of I. Now, since the child is an exact replica of the parent and the value of I in the parent as well as the child would be the same. Thus, when we execute this program, we get something like this: both the child as well as the parent print the value of I as 23. Now, let us modify this particular example and see what happens when we add this particular line. So, what we have done over here is that we have incremented I equal to I plus 1 only in the child. Note that in the parent process there is a sleep 1 over here. So, which means that we are giving sufficient time for this I equal to I plus 1 to be executed by the child, and only then will this printf of the parent be executed. So, what do you think would be the output of this particular program? So, one would expect that the child would print a value of 24, since we have incremented I by I plus 1. So, that is 23 plus 1, and also the parent would also print the value of 24. However, when we execute this program, we get the child has the updated value of 24, however, the parent still has the old value of 23. Now, given that both the parent and child point to the same page frames in the RAM, so how is this possible? So, we will look into why such a phenomena is happening. So, this phenomena occurs due to a technique known as copy on write that is implemented in the operating systems. So, when a fork system call is executed in the OS, all parent pages are initially marked as shared. The shared bit is present in both the parent and child page tables. When data in any of the shared pages change, the OS intercepts and makes a copy of that page. Thus, the parent and child will have different copies of that page, and note that this page is highlighted over here. So, that means only that page would be different in the parent and child, while all other pages would still remain the same. Let us see how copy on write works with our example. Let us say that the value of I is stored in this particular page frame, which is pointed to by the parent page table as well as the child page table. When the child process executes and increments the value of I to I plus 1, that is the value of 23 is incremented to 24, and the new value is written back, the OS would intercept the write back and create a new page for the child. So, the I of the child process would be present here, and it would have the new updated value of 24, while the original I value of the parent would be present over here and would have the old value of I, that is 23. Further, the corresponding page entry in the child's page table would then be updated. So, what is the advantage of cow? We will see in a later slide. Now that we have seen how to clone a program, we shall now look how to execute a completely new program. Executing a new program comprises of two steps. First, a fork system call needs to be invoked, which would result in a child process created, which is an exact replica of the parent process, and then an exec system call needs to be invoked, which causes the new program to be executed. So, let us take this particular small C code. So, what we see is that initially a fork system call is invoked, which should return a PID value and create a copy of the parent process called the child process. Now, in the child process, the PID has a value 0, therefore, execution will enter this else part. Now, in the child process, we invoke a system called exec. In this case, it is a variant of exec known as exec LP, and pass several arguments. Of these, the most important one of course is the executable file name. In our case, we are trying to execute the file a.out. Okay. So, when this exec system call is executed, it triggers the operating system functionality. So, what the OS does is it finds on the hard disk the exact location of the a.out executable. Then it loads on demand the pages required to execute a.out. So, let us actually look at this more pictorially. So, what happens when we invoke the fork? So, fork, as we know, would create a child process which is an exact replica of the parent. So, what we have seen is the child has its own page tables, but all entries in the page table identically map to the same page frames as the parent. Now, let us see what happens when the exec system call gets invoked. So, when the exec system call gets invoked, the operating system would find the program or the executable location in the hard disk and load blocks from the hard disk into page frames on demand. Thus, for instance, when we start to execute the new child process, it would load, for instance, the first block of the new child, and then on demand whenever required new blocks would be loaded into the RAM. Subsequently, the child's process's page table would also be updated as required. So we see two things that occurs. First, we notice that whenever a new block or whenever the child program that is being executed has a new functionality, a new page frame gets allocated to the child process. However, the functionality which is common to both the parent as well as the child still share the common pages, for instance like this. So, let us see what the advantage of copy on write is. So, as we know, most programs are written with a large number of functionality which is common. For instance, many programs we know would have would use printf or scanf or standard library function calls like fread, fscanf and fprintf and so on. Since a new process is created from a parent by first cloning the parent and then executing the new program, thus a lot of the functionality of the parent will also be present in the child process. Now, since pages are replaced only on demand in the child process, the common functionality or the common code which is present in both the parent as well as the child process is still shared between the two processes. For instance, printf which is present in the parent process and the printf which is present in the child process still point to exactly the same page frame in the RAM or in the physical memory. So, what this means is that although you may have like 100 different processes running on your system and all these processes may use a common function such as printf, in RAM as such there will be only one copy of printf present. All processes would then use their page table to point to this particular page frame which contains the printf. So, we have seen that creating a new process first requires a fork and which is then followed to by an exec system call. So, every process in the system is created in such a way. Therefore, we get a tree like structure where you have a root node known as init.d and every subsequent node represents a process running in the system and is created from a previous process. For instance, the process compass is the child process of genome session. Genome session in turn is the child process of init and so on. So, eventually we reach the root process which in this case is known as init.d. If you are interested, you can actually look up or execute this particular command, that is ps-tree, from your bash prompt, which lists all the processes in your system in a tree like structure. So, we have seen that every process in the system that is executing has a parent process. So, what about the first process? So, it is the only process in the system which does not have a parent. So, who creates this process? The first process in Xv6, the first process is present in init code.s, is unlike the other processes because this particular process is created by the kernel itself during the booting process. So, in Unix operating systems, the first process is known as is present in /sbin/init. So, when you turn on your system and the operating system starts to boot, it initializes various components in your system and finally it creates this first user process which is executed. So, this is sometimes known as a super parent and its main task is to actually fork other processes. Typically in Linux, the first process would start several scripts present in /etc/init.d. Now, let us look at the code init.c which is part of Xv6. So, essentially this particular code forks a process and creates a shell sh. So, this is a snippet of the code. In particular, I would like you to notice this particular loop, this particular for loop, which is an infinite for loop. So, it runs infinitely. Its only task is to fork a process creating a child process, and in the child process it runs exec sh, which is a shell with some argument. Then it waits until that particular spawned or a forked process completes, and then this thing continues forever. Now that we have seen how processes are cloned, how a new program is executed, let us see how to terminate a process. A process gets terminated by something known as an exit call. So, for instance, let us go back to our example, and in the child process we actually run the executable a.out or execute which then gets executed, and this is followed by an exit 0. So, this exit is invoked in the child process, and the parameter 0 is a status which is passed on to the parent process. So, this particular way of terminating a process is known as a voluntary termination. In addition to the voluntary termination, there is also something known as an involuntary termination. In such a termination, the process is terminated forcefully. So, a system call which actually does that is the kill system call, which takes two parameters, PID, that is the PID of the process which needs to be killed, and a signal. A signal is an asynchronous message which is sent from the operating system or by another process running in the system. There are various types of signals such as sigterm, sigquit, sighint, and sighub. When a process receives a signal such as sigquit, the process is going to terminate irrespective of what operation is being done. So, another important system call with respect to process termination is the wait system call. The wait system call is invoked by the parent. It causes the parent to go to a blocked state until one of its children exits. If the parent does not have any children running, then a -1 is returned. So, let us go back to our example over here, where the parent has forked a child process, and in the parent process it obtains a PID which is equal to the child process's PID. So, this would result in the parent actually executing this statement which is a wait, and it would cause the parent process to be blocked until the child process has exited. When the child process exits, it would cause the parent process to wake up and the wait function to return with a return value of PID, which is the child process's PID. So, in order to obtain the return status of the child, that is in this particular example 0, the parent process can invoke a variant of wait such as this. So, in this particular variant, a pointer is passed to status, in which the operating system will put the exit status of the child process. When a process terminates, it becomes what is known as a zombie or a defunct process. What is so special about a zombie is that particular process is no longer executing. However, the process control block in the operating system will still continue to exist. So, why do we have this concept of zombies in operating system? So, zombies are present so that the parent process can read the child's exit status through the wait system call. When a particular program exits, its exit status is stored in the PCB present in the operating system. So, when the wait system call is invoked by the parent process, the PCB of the exiting child process would be read and its exit status would be taken from there. When the wait system call actually is invoked by the parent, and the extra zombie entries present in the OS will be removed. So, this is known as the process reap. So, what happens if the parent does not read the child's status? In such a case, it will result in a resource leakage, and the zombie entries in the operating system will continue to exist infinitely. So, these are eventually removed by a special process in the OS known as the reaper process. The reaper process periodically runs and recovers any such zombie process states present in the OS. When a parent process terminates before its child, it results in what is known as an orphan. For instance, let us consider this as the process tree, and in particular this is a process with a parent over here. Now, suppose this particular parent exits while the child continues to execute, or then the child is known as an orphan. In such a case, the first process or the sbin init process will adopt the orphaned child. There are two types of orphans. One is the unintentional orphan, which occurs when the parent crashes. The other is the intentional orphan, sometimes called daemons. So, an intentional orphan or a daemon are processes which become detached from the user session and run in the background. So, these are typically used to run background services. So, now let us look at the exit system call from an operating system perspective. First, we notice that the sbin/init, that is the first process in the system, can never exit. For all other processes, they can exit by either invoking the exit system call or can exit involuntarily by a signal. So, when such a process exits, the operating system will do the following operations. First, it would decrement the usage count of all open files. Now, if the usage count happens to be 0, then the file is closed. Then it would wake up parent, that is, if the parent is currently in a sleeping state, then the parent would be made in a runnable state. So, remember that runnable state is also known as the ready state. So, why do we need to wake up the parent? We need to wake up the parent because the parent may be waiting for the child due to the wait system call. So, we need to wake up the parent so that the parent could continue running. Then, for all the children that the exiting process has, the operating system will make the init process adopt all the children, and lastly it would set the exiting process into the zombie state. So, note that certain aspects of the process such as the page directory and the kernel stack are not deallocated during the exit. These metadata in the operating system are deallocated by the parent process, allowing the parent to debug crashed children. That is, suppose the particular process has crashed, the page directory and the kernel stack will continue to be present in the operating system, thus allowing the parent process to read the contents of the crashed child's page directory and kernel stack, thus allowing debugging to happen. Now, let us see about the internals of the wait system call. So, this particular flowchart is done with respect to the x86 operating system. When a parent process in the user space invokes the wait system call, these following operations in green occurs in the operating system. So, first there is a loop which iterates to every process in the p table and checks whether the process p is a child of the current process. So, if it is not a child, then you take the next process in the p table. However, if it happens to be a child, then we do an additional check to find out if it is a zombie. So, if the child is not a zombie, then the parent process will sleep. However, if the child is a zombie, then we deallocate the kernel stack and free the page directory, and the wait system call will return the PID of p. So, in this video we had seen about the process, how it is created, how it exits, and about system calls such as the wait, fork and exec system call. Thank you.